Hi, Dr. Revis here. In this video, I will discuss basic Beer's Law concepts with emphasis on laboratory experiments. So what is Beer's Law, or what does Beer's Law describe? Beer's Law, which is also known as the Beer-Lambert relationship, describes the relationship between the absorbance of a solution and the concentration of that solution. The amount of light absorbed is proportional to the concentration of the solution. In other words, Beer's Law allows you to determine or measure the concentration of a solution based upon the amount of light that is absorbed or transmitted from the sample solution. The amount of light absorbed is proportional to that concentration and is given by the expression absorbance equals molar absorptivity constant times the path length times the molar concentration. The absorbance is a unitless value. Molar absorptivity is given in reciprocal molar concentration, reciprocal centimeters, or liters per mole centimeter. The path length is typically given in centimeters. The concentration is in moles per liter or a molar concentration. So how does it work? A single beam passes through a solution containing a sample. When that light passes through, the sample absorbs some of the light and transmits the remainder. Therefore, the difference between the incident light, which is the incoming light, and the transmitted light is proportional to the concentration of substance in the solution. As the concentration of the sample increases, the amount of transmitted light decreases. The decrease is because the amount of light absorbed by the sample molecules increases. This affords a method of quantitating the concentration of the sample. A single beam light source passes through the solution, which means that the difference between the incoming incident light and the exiting light is what's being actually measured. So, the transmittance or transmitted light is defined as the fraction of incident light which is transmitted. Absorbance, or the optical density of the solution, is directly proportional to the concentration of the absorbing substance in the homogeneous solution. It can be expressed by a logarithmic function that relates the percent T to the absorbance. That expression is A equals 2 minus the log percent T. And why is that so? T equals the ratio of transmitted light to incident light. In other words, the ratio of the amount of light coming out of the sample to the amount of light being shined into the sample. That relationship is oftentimes expressed as a percent. Therefore, the percent T will equal 100 times that ratio of transmitted light to incident light. Because we know the relationship between absorptivity and transmittance, we can set up a series of other equalities to derive various useful forms of the Beer's Law equation. Measurements involving Beer's Law are taken using a spectrophotometer or colorimeter. A spectrophotometer or colorimeter measures the absorbance of light at a specific wavelength for a solution. The absorbance follows Beer's Law principles, which states that the absorbance of a sample depends on the molar concentration, the path length, and Epsilon is the molar absorptivity constant for this solution. The molar absorptivity constant is also known as the molar extension coefficient, epsilon, for the dissolved substance at a specific wavelength. The extension coefficient is oftentimes experimentally determined using plots and graphs. In a plot of Beer's law, for example, the slope, which is absorbance divided by concentration, equals what's known as molar absorptivity. Therefore, the molar extension coefficient, epsilon, can be experimentally determined by measuring the absorbance of 3 to 4 dye concentrations and plotting the data using Beer's law principles. In other words, we find the slope, which is epsilon times the path length, and then we can use the known path length to evaluate epsilon or other variables by the equation C equals A over slope equals A over epsilon L, where again C is the molar concentration, A is the unitless absorbance, and epsilon is the molar absorptivity constant for this solution. And L is the path length for that instrument. When we do that, we can establish a calibration curve that allows us to evaluate unknown sample concentrations. We show you an example of that calibration curve here, where we have absorbance measured against the molar concentration, and for teaching purposes, we converted this to percentages of that molar concentration. Once we establish a best fit line, we can evaluate the slope, and we know that slope equals epsilon times the path length. We can then use that data and the Beer's law equations to evaluate any of the variables, and in particularly, we can find the molar absorptivity constant, epsilon, for this solution. If this is being done in Excel, Excel will give you the equation of a line. You will look at the slope in front of the x value, and that slope will be equal to epsilon times length. And since the path length will always be known because of the standard for each instrument, you can evaluate epsilon or any other unknown variable. But this calibration curve allows you to now measure the absorbance of a sample and determine its concentration by extrapolating, as we've shown you in this illustration, on the red dotted line. If the absorbance is red at, for example, 0.4, we can extrapolate across, and we coincidentally find this to be a concentration of 40% of the molar concentration. In the laboratory experiment, the actual molar concentrations would be known. The Beer's law equation can be used to carry out other calculations. Let's do a problem. Using a cuvette with a length of 1 centimeter, the absorbance of 0.05 moles per liter solution at a wavelength of 280 nanometers was 1.5. What is the value of the molar absorptivity constant, epsilon, for this solution? We take the Beer's law equation, A equals epsilon, length times concentration. We arrange it as shown here, where epsilon equals the absorbance divided by the length, path length, times the concentration. We then put in the values of 1.5 for the absorbance and divide it by the path length times the concentration, and we obtain 30 liters per mole centimeter as the value for epsilon at this wavelength. It is very important to note that epsilon is specific for the solution at a specific wavelength. We can also solve Beer's law problems by using slope information that we get from graphs. This is a very common practice for general chemistry laboratories. Here's the problem. The absorbance of a 0.2 molar solution is 0.27, and a 0.3 molar solution is 0.41 using a spectrophotometer with a path length of 0.5 centimeters. What is the molar absorptivity constant for this solution? We take the Beer's law equation, A equals epsilon LC, and since the slope is equal to epsilon L, therefore we can say that epsilon LC equals the slope times C, which is the concentration, and that too can be used to evaluate the absorbance. We will take these equations and we will use it to solve for the extinction coefficient or the molar absorptivity constant. We'll do this in 2 steps. Step 1, the absorbance values are Y values, while the concentrations are X values. Therefore, we will use the slope equation for a line, where Y2 minus Y1 divided by X2 minus X1. We evaluate this by putting in the values 0.41 minus 0.27 over 0.30 minus 0.2, and that gives us a value of 1.4 for the slope. We note that the slope equals epsilon times the length. That brings us to step 2. We'll use the slope and the path length to evaluate epsilon. So, since the slope equals epsilon L with a path length of 0.5 centimeters, therefore epsilon equals the slope divided by the path length, which is 1.4 divided by 0.5 to give us a final answer of 2.8 liters per mole centimeter. Note, in working this problem, the units were omitted for simplicity. This is the same data that you would get from graphing it and using an Excel program to give you the equation of a line. There you have it, basic Beer's law concepts with emphasis on laboratory experiments.